Hi everyone. Today I'm going to talk about JVM performance engineering. These are really some methodologies, approaches, and process that I have used over the years as I was learning to be a JVM performance engineer, and then as I gained expertise in the field. So I hope to take you with me on this journey because I'm going to talk about JVM and very specific. I'm going to talk about HotSpot, which is the OpenJDK Java virtual machine. So most of my examples and advice would be with respect to the JVM, but I'm going to talk about a holistic system-wide approach. So let's get started. When we talk about software engineering, we usually think about it in two different ways. Okay. So, what are we building, as well as how are we building it? Okay. So, basically, the what is the functionality, like how, and how does it do it? That's the operation. Okay. So the functionality would be defined by the software design and development process, right? So you have this whole life cycle for your software and your the stack that you have, and that would be the functionality, and then the other side of things, like the operations, how do we execute? How do we evolve? How do we make our this architecture make performant, or any kind of abilities that we want to improve, like scalable? So that becomes your architectural requirements. So today I'm going to talk more about the architectural requirements and kind of zone in on the functional little bit as a side process, but mostly in the performance realm. The other way, like I was talking about, to look at it is functional requirements and non-functional requirements. So whatever doesn't fall under functional, that goes into non-functional. So let's look at the non-functional requirements very quickly. You know about performance. Today I'm going to talk about performance. So of course, performance is my is the first bullet point here. The next is security, very important, but I'm not going to talk about it today. Scalability and performance actually go hand in hand, because now we're talking about distributed systems, we're talking about cloud, we're talking about going maximizing your utilization. So all this is falls under the scalability umbrella, but it goes hand in hand with performance. Usability, portability, observability. So again, observability also goes together with performance, as you will see that some of the tools that I will talk about actually fall in the observability realm, especially like the Java Flight Recorder and such. And complex system, you need to understand the internal states, and that's where observability shines. And like I said, we will talk about it shortly. So let's dive into performance. First, we need to understand the what of performance. What is performance? And then how, like how do we go about understanding the performance, and how do we go about understanding the requirements? Okay. So what is performance? You go ask your stakeholder about performance, and they'll say something like, I want everything to go faster. I have this system. I just want it to go faster. But like, what does that even mean, right? It just doesn't make sense, right? So what we're going to do is going to find a process or define an approach that makes sense. So how do we do that? We do that by asking questions. So the questions are, so this you could ask directly to your stakeholder. You could say, what makes your users happy? What makes them happy? And any current issues that need to be tackled. So right now, so if you have an existing software system and it's functioning okay, but that is only at 90% utilization, and for some reason, whenever there are spikes in the system, it doesn't handle them well. Of course, because you're already at 90% utilization of the system, the spikes may put you over the edge, which means that you may have some of the bottlenecks that you would have never encountered before are now surfacing, right? So that kind of stuff where, oh, it doesn't handle the spike in traffic, that is something that is a current issue in the way we are operating, in the way we are scaling, or in the way we are utilizing. And so we need to understand that better before we go into further optimizations. Okay. So now that we have asked questions, the next thing is to define and understand different metrics. So when we could talk about performance, we'd always guarantee a quality of service, right? And this quality of service is something that your end user understands and expects of your system, right? So first, we need to understand what quality of service. So as a performance engineer, when we go into and trying to make a system more performant, we need to understand these quality of service. What is the guarantee that we have given the end user? And then we need to make sure that we can define these quality of service metrics in measurable terms, right? Up until now, we're talking about happiness. We're talking about these terms that in reflect satisfaction. But how do we talk about satisfaction in terms of something that's measurable? So that's the job of a performance engineer. So when we define these quality of service metrics in terms of something that's measurable, these are called your service level agreements. So if you're lucky, your the system, the stakeholders that you're trying to help are actually already ahead of the curve, and they already have some service SLAs defined for you. If not, then you sit down and define SLAs with them. So, so what is this next step? Is the next step is very simple. You gather your stakeholders and define success, which means get your quality of service in defined SLA terms. Okay. Okay. So let's start there. So our success criteria for performance requirements or service level agreements can be defined in terms of either the footprint of the system or the footprint of the subsystem, right? Maybe that's the one that we want to improve, or response time or throughput. And then it could be capacity, utilization, and of course availability. So this is these are just a few things that I've gathered over the years that are most important and that have surfaced enough during my consultancy or during my work with any of the cloud providers or like hardware vendors, that I can understand that these are the most important things and there are definitions that you can provide for each of these things. Because I want to go and talk about methodology and go give examples and the time that we have, I'd like to go ahead and kind of talk more targeting one of these, okay? Target response times. So when we're talking about performance requirements and we're talking about success criteria, remember I talked about getting your SLAs. Talking about response times, you want to improve response times, you want to make your end users happy. So we will talk about response times metrics as either average or max or worst case, 99th percentile, etc., etc. The basically what I'm trying to say here is that one metric is not going to cover it. So I also hear people talking about 5 nines, right? When you're talking about 5 nines, what are you missing, right? And here is an example of from a real life work that I've done with respect to improving response times. But this is how I got to go through the process and understand the actual problem. Okay, so what I did was like ask for these SLAs. I defined these SLAs, and then I asked for them to be measured. Okay, and this is a distributed system. There's like 4 different systems serving. So it's like a distributed data system. So, what at first, when you look at it, you have these 4 systems identified, and then you have, because it's a long running system, there are a lot of GC events, right? And they look like, if you look at system 1 to 4, they're kind of in the similar ballpark, right? So you have about 34,900 events at a minimum, and then it goes all the way up to 40,000 events, right? And for those events, you see the scale of the GC pauses, and which also the GC pauses reflect as the system pause. And so minimum, it's only 7 milliseconds. This is way below their threshold, right? So the threshold was the 5 nines. They wanted it to be less than 1 minute, right? And their absolute, like, where the break even happens is like 5 minutes. So here we go. Now minimum time doesn't any problem, right? And it doesn't showcase anything. So then, of course, they went and looked at the average milliseconds. Okay, and average, as you can see, is in the 320 milliseconds range. Again, not threatening at all. You go to Then you go to 1 second range, where your 99th percentile translates to about 1 second, right? But again, this is not threatening at all. And they couldn't understand what was the problem. Why were the end users having issues? Because these are GC pause times, but they translate into the system pauses. So the system is a latency sensitive system, and these services are kind of like really counting on the tail latencies to be low. So 99th percentile is still not able to capture your tail latencies, the worst tail latencies. So what I did is I asked them to add another metric, which is the maximum milliseconds. So now you can see your system 4 actually had issues where you had up to 20 seconds of pause time. So basically, it was encountering 5 full GCs and 10 evacuation failures. And that was propagating down all the way. The tail latencies were getting incrementally bad, and it was propagating down in the system to where their fail-safe mechanism was getting triggered, and basically this 20 seconds was actually translating into more than 5 minutes of delay, just because of the depth of the call stack that they had, of the stack of the system that they had. So things that very well from the JVM perspective are the pauses. So if you're not capturing all the pauses, that can lead to tail latency increase in the system and drive your system to its knees. So there's an example right there. We were talking about, just when I had the issue, we were talking about different approaches, right? So I showed an example, and then I want to show you how I got to this conclusion and how we diagnosed the process. So here I'm going to start with talking about Java engineering approaches and process here. Okay, so I here's an application stack. It's a very oversimplified stack, but I do know. So it could be a database application. It could be a Java-based service, or you're doing some I/O work and you're using Netty. But all this kind of forms just the way it is. Your application stack runs on top of the JVM. which has its own runtime environment. And then you have the operating system. Of course, you can have all this in a container. You could have the container in the cloud. But eventually, you have the operating system and the hardware. So if you are in the cloud, your operating system could have host and guest OSs and stuff like that. But very simplified stack will look something exactly like I've shown you here. Okay. So let's start with the application and its ecosystem, right? So what does that mean? So like I said, the application could be any of your services, your microservices, your services that actually interact with your database and other such things. You could have actually an application server. You could be hosting an application server. So that could be your application and its ecosystem based on whatever services you're offering with respect to your application server. Apart from your services in your server, like your Java process, you could actually be having various other interactions that are happening, and that constitutes of your application's ecosystem. So you could have utilities, you could have libraries, you could have frameworks, you could have database, like I said, you can with all those things. What about any other service engines, right? So I mentioned Netty. You could have Kafka streams, you could have document schemas, any of those things that actually constitute as the application and the ecosystem layer, okay? Then comes the JVM and the runtime environment. So there are lots of information that your JVM and the runtime environment can provide you. And this helps you in various things. You're thinking about startup, you're thinking about optimizing latency with respect to startup and warm up and the entire existing phase of your JVM loading process, your Java application load setup process, right? So you want to know about the class loading stats, of course, which can be provided to you by the Java runtime environment. But also, what about the compilation itself? What about the JVM execution engine, right? So that information is also provided to you by the JRE. And then you move on and then you're doing this long time runs. You're running over 4 hours, but you're having some interrupt or some issue with respect to your pastime goal. So your max time goal is not, or maybe even you start seeing issues right from your 5 nines or the 99th percentile, and you're seeing this trend. So what do you need for that? You need your garbage collection logs and other related stats with respect to garbage collection. Then there is, of course, you're talking about the JVM ecosystem. So we are talking about concurrency and threads and the deployment and the starvation, all those things. So that is also provided to you at the JVM runtime level. So you get the thread stats, your locking stats, and and when you have an ecosystem, when you're dealing with database, when you're dealing with Netty, when you're dealing with all this fun stuff, you're doing certain JNI pool and buffering. So that information also you have to extract from your JVM layer, and so on and so forth. Next comes the operating system. So you get the system-wide stats, the kernel stats, like anything that's not JVM or that's not with your services, then that falls outside of that. So it could be interactions between these subsystems that you have, and that information will be provided to you by your operating system. So you can do CPU stats, you can gather locking stats actually, because threads, we're not yet into the lightweight threads model, the green threads model. So we still are dependent on the operating system. So we need to look at the locking stats, the thread stats, the IO stats, and so on and so forth. Finally, hardware. Everything, even in the cloud, runs on a physical device, right? So you need to understand what physical device that you're running on. So if you're using some specific instructions, you want to optimize vectorization, you want to optimize, your floating point, or your security or AES and other, so that your hardware is utilizing this or supports those instructions and services. So the other part of it is that you're trying to drive throughput, right? You're trying to make sure that your traffic is getting handled correctly. So then you need to understand memory bandwidth, like how much is your underlying hardware able to support? How much can it consume? The core utilization, are you trying to be efficient in respect to, the cores that are offered underlying? And then these things they get really deep. The more you look at these hardware subsystems and how they interact with each other, it gets really deep and interesting. But I'm just going to list these things and move on. So now we have the stack. We understand what information we can gather from each stack. So what do we need to do next? We know some things. We know our application. We know our application stack. We know what we need to gather. But there's some unknowns, right? So the way I define known unknowns is that we have the domain knowledge because we understand the subsystems like I just showed you. But we kind of need more detailed information to identify the bottlenecks. How do we get to the performance goal that we have set for ourselves? There are some bottlenecks, but we don't have visibility into these bottlenecks. So that's when we adopt a methodology. So the same subsystem that I have shown, the same stack, right? I'll talk about the top-down methodology, right? So it's very simple. You know your application. You're trying to improve your application scalability, right? So everything else underneath the application is the platform that your application is working on. So your application the best. You're an application developer. You have deployed the application. You understand the issues with the applications. You have the control of various subsystems and the ecosystem of the application. And underneath it, you have, say, you're working on JDK 11. So you understand that. But the JDK 11 on a Windows operating system, on an Intel machine, you understand the entire stack. But that constitutes from your application level performance diagnostic tooling and other things, those constitute as a platform. The next is the bottom-up methodology. Again, we will bring the same analogy, like you have the application, but if there's anything in the platform that you want to improve. So for example, I have an application, but I want to plug in JDK 17 now. I'm already at JDK 11. I want to plug in JDK 17. That's when you try the bottom-up approach. Anything that you want to change at the platform level or anything you want to test and improve at the platform level. I want to compare Windows performance to Linux performance because I want to see how that goes. Or I want to compare Intel to, say, ARM. So then I go, or there are changes in the JVM. I want to try a new feature, right? So all those things actually fall under the platform umbrella. So that's when you take up the bottom-up approach. The good news is that no matter bottom-up or top-down approach, you will always follow this iterative process that I'm going to talk about next. Sorry, once again, the same issue with my slide deck. I apologize so much. All right. So the step one in the iterative process is to monitor, okay? And we'll detail each steps quickly. Step 2 is to profile. Step 3 is to analyze. Step 4 is to tune and apply. Okay, let's talk about each step here. So, monitor. Simply what I say is that you have a system under test. So if you're doing the top-down methodology, your system that you want to improve is your application and its ecosystem, right? So you have that. That's called your system under test. If you are doing the bottom-up methodology, then you're trying to improve anything in the platform layer, right? So that's your system under test would be the JVM the new JDK that you're trying, or your new OS that you're trying. And so all those things, that's called your system under test. So we need to plot and monitor statistics from that perspective. Okay, so we gather and compare. Something very interesting about performance monitoring is that it is non-intrusive, right? You're collecting data and you're gathering observations, and you're kind of formulating your next step, right? So why not have that enabled from the very beginning? Get insight into your application and the platform from the get-go of your deployment, right? So what how that helps is that you can establish patterns. What is normal, right? My application is working at 80% load, and say that is your normal pattern. But then when I have spikes, then that becomes an abnormal pattern. Thanks to monitoring, you can identify these normal and abnormal patterns. You can have timestamps that tell you exactly when these abnormal patterns happened, how long they lasted, and so on and so forth. So that performance monitoring is really, really important and should be enabled from the very beginning. Performance monitoring also feeds into performance profiling. It kind of helps guide where do we need to deep dive, because performance monitoring is present everywhere throughout. But these abnormal patterns may, or high utilizations, or if you want to try to go scale, you want to figure out where can I apply scaling patterns, right? So again, performance monitoring is step one, and then it feeds to the other steps. I'll quickly go through this. This probably everybody knows. There are different tools for performance monitoring, active, passive, offline, even online now. People do continuous monitoring and stuff like that. So you all know this. I'm going to move forward. Um, Tools for monitoring. You have the JFR counters that are inbuilt. You can gather them and then do offline analysis. You can do print compilation, all these things. I've not put the GC, the new unified stuff, because then it gets a little bit confusing. But what I'm saying here is like target the logs that you need, and that all should be captured during monitoring phase. Okay. Tools from Linux and Windows perspective, they all offer beautiful system-wide statistics, CPU-wide statistics, memory-wide statistics. They offer I/O. They offer logs. They offer contentions. They offer so all these things. I won't go into details of those, but very important monitoring tools. Now let's go to step 2 and step 3. I have all the data, right? I just collected I've been collecting that for a long time, and I've established my patterns already, right? And that's where your patterns, either you're removing a bottleneck, or you're trying to add some improvements and scalability stuff to your process. And so the next step I want to do is profile these hotspots that I identified, and then analyze those hotspots. Okay. A word of caution here. Profiling tools are very different than monitoring tools. And people always ask this question, right? What's the overhead? Like, trust me, profiling tools overhead is at least more than 5%, right? So when I say overhead and intrusive, that should give you an indication that we don't enable it from the get-go. We don't keep it on, we just use them to target our optimizations. So what you can do is gather your monitoring data, and then you deep dive into the profiling data, kind of to get more focused investigations. And the way you do it is you gather a slice. So I've had issues here, or I want to improve this particular slice. So you gather the slice from, say, the top-down methodology, because you want to improve and scale your application. So you gather a slice from the top, from the application all the way down to the hardware. Or if it's a bottom up, then you gather the slice from when you saw the problem between, say, Windows and Linux. There's a performance difference, and you see these, the monitoring shows you that, hey, we're spending more time here on Linux, whereas we're spending more time here on Windows. So gather slices of right there, and then go and profile. Okay. because profiling is intrusive. Profiling tools. I've listed a bunch of stuff here. Um, but I won't deep dive into it. One of the things I trust a lot and I've worked with a lot is Performance Analyzer. I've worked with VTune. And then if you're just targeting Java application, then you have Visual VM, NetBeans Profiler, JConsole. I will not be able to show everything in detail here, but I have some examples. And then, please reach out to me and I can help. If you have not used these tools, I will talk about them, separately outside of this presentation. So, tuning, right? Tuning the JVM is what we got today. And this is from an old presentation that I had. And what I want to say is that a lot of the JVM and GC heuristics are really important, and they're kind of geared towards, at least in OpenJDK, they're geared towards different applications and different bottlenecks that they're trying to handle. So we have latency sensitive garbage collections, we have throughput driven garbage collections, we have garbage collector that is, kind of helps with footprint by not, the more concurrent structures that you have, the more dependent data structures that you have, the more maintenance that you have, it kind of expands on the footprint. So if you size your heap properly and you get the GC algorithm correctly chosen, then you are on the right path, right? So that's step one. And then how do you one of the things that you should know about OpenJDK also is that most of the garbage collectors, in fact, very soon, all of the garbage collectors are going to be generational. So the whole concept of generational is that, objects die young, most objects die young, and then you kind of age them in the young generation and promote only those. So if you apply those principles like age appropriately and promote only the long lives, then that is kind of setting you up for success already. Couple of other things to think about is like, are we utilizing the GC worker threads, so if you have stop the world, and even if there's a latency sensitive garbage collector, it does have stop the world GC events just for bookkeeping, even though like for in ZGC, it's guaranteed to be less than, I think it's sub milliseconds now. So, but even then, it does have stop the world and everything. So if you're having scaling issues, like go look at your GC worker threads and help out start helping out from there. You have GC concurrent works, like for all the new concurrent GCs that you have concurrent GC workers, and then sometimes you may have to work with them, and then as sophisticated GCs come into play, you have the concurrent workers become really, really important, because then you don't want to overload your application threads, because sometimes the GCs will enlist the application threads. So you want to keep the work in the GC domain, right? That their GC is good at doing its work. So GC has worker threads. Let GC do the work. Um, Yeah, there's another thing that I have recently found with respect to, I was working with the ARM systems, ARM architecture, and compressed surprisingly can be very helpful, and that just basically helps with respect to one of the ways you can get more compressed oops is by expanding your compressible heap space. So what I mean is that you can change object alignment and then get more compressed heap space based on the alignment, because it kind of helps with the way your cache lines, the CPU, your underlying hardware architecture, how the cache lines can bring in data, and how the Java objects are spaced. So there are optimization in the Java object headers and other optimizations that can put, like string density and something like that can put objects together. But things that can help with respect to mechanical, like the hardware, underlying hardware, sympathizing with the underlying hardware, you got to be mindful of that. So that will help with your tuning as well. Uh, when you have large pages, you may want to enable always retouch, and sometimes using large pages. And remember, this is again tying in with your understanding your hardware, right? Most hardware, the CPUs offer different size of this is called translation look-aside buffer, which is like a cache inside of a CPU. It has these pages that it can access, and they have different sizes. So think of your Java heap being able to access those different sizes, bigger sizes. So your memory, the cache of this page sizes are kind of already there. So the turnaround is quick. So we're kind of again sympathizing with the hardware. So your GC is able to do all these things. Tune your code, make sure that you have ramp ups and ramp downs as you're working with your application. Sometimes you're thinking that you're in steady state, but there were some a burst of deops, which is like a terminology for the JIT compiler. So why did the deops happen? Like, what did we not ramp up? Did we just get a different code? You're doing deployment on the go, production deployment and everything like that. And something may have caused certain DEOP storms to happen. So understand your application in tune to make sure that you understand at least the ramp up and ramp down phases. And if something needs to be ramped down before it can ramp back, and again, you have to be responsible and understanding and available for that. Object age and retention. You have to understand how long you're keeping objects. You may be creating temporary objects, and that may not be a problem, but it could get problematic when your object allocation rates are really, really high, right? So, how long does the object live, and how long am I keeping it alive, and stuff like that. You have to be aware of that. What forms your live data set? So you can keep your objects alive longer, but if they are just transactional object, they're not called a live data set. They don't form you long. They're not long lived. They're just medium lived, or they're transactionally irrelevant, right? So if you promote these transactionals, they will go into the OLGen. You will have trigger some form of OLGen collection, and that may or may not be beneficial depending on what you're targeting. Also, confirm you're measuring the right thing, right? What does that mean? That means that if I'm trying to get information on the data, like I'm trying to get information on the latencies, then I am capturing the right metrics, and I'm measuring the right metrics, and not trying to conflate. Like, for example, you're a database and you're trying to scale your database. For scalability, you want to talk about utilizations. Utilization will drive your QPS higher, right? You improve utilization, you can push in more queries, and you can, your queries per second increases. But if I'm only measuring queries, I'm not measuring where my bottleneck is, which is in the utilization aspect of it. So I need that information. I need to understand my utilization before I can drive my queries. So stuff like that. So, 3 things. You know what you're stressing, like the system under chest, right? If you have the right workload, because you're doing the top-down methodology, you already have that. Otherwise, if you're doing from the bottom up and you have you need to get the right application to stress that platform, right? So either you have it, or you go and get it, or write a benchmark, for example. Get the right tools. I've listed a lot of tools, but also make sure that if you don't have the right tools, if you don't have the right observability, if you don't have the right diagnostics, you don't waste any time and get to write the tools that you need for your performance analysis. So, if you're stressing the CPU, gather the performance counters, gathers misses, cache misses, and all this. So these are something very specific to the hardware CPU, the hardware core. This is very important if you want to get keep up your utilization and other information. So because Java does memory management and the garbage collector works along with your application, there's a lot of issues that noise, we can call it, that can affect your CPU because we're working in the Java domain. So keep a track of that, and you can drive your CPU utilization higher with respect to what you're stressing. What about memory, right? There's a lot of information you can gather with respect to memory. You can do, like when you're doing capacity planning, you want to realize the sustained bandwidth, for example. So make sure that you're able to do that, right? To figure out your sustained bandwidth and bandwidth at load, bandwidth at 2x load, bandwidth at like wherever you want to go. So as you want to slow down, you're going to make sure that you're the right metrics. Okay, so these are some considerations for that. With respect to the JVM, we already talked about certain things. So, for example, you want to try a new GC, for example, right? So again, let's look at what we can do. You can figure out what are the different phases of the garbage collector, right? How is that affecting? And recently, we were looking at different garbage collectors, and then there was ZGC, there was Shenandoah. So people are trying to move either from CMS to G1 or from CMS to ZGC or to Shenandoah. And then there's a vast difference between where CMS was and where the new GCs are. So if you're not educating yourself with respect to the GC phases, what are the work queues and different things, there is also like the JNI stuff, which is different, which is respect to the pinning versus not pinning. So there's a lot of internal pressure, based on your application. There are different trigger points within garbage collectors that you need to understand. And this is something, just listing all that. Now with that, I want to move to a couple of examples. I tried to put it all together into something that could be interesting to most people out there. Memory leaks, okay, especially in Java applications. And it's kind of like funny when you think about it, right? Because we're talking about Java, right? Java does automatic memory management, right? Like you could say, hey, I didn't do it, like because I'm just writing an application in Java, and Java has this garbage collector, and I just spoke about a lot of them. So how can there be a leak? Because Java is doing the allocation, Java is doing reclamation. Here, just quickly want to talk about allocations are really, really fast in the JVM, in OpenJDK, because we have something called thread local allocation buffers. So they're mostly lock-free, so each application thread can actually allocate objects in their thread local areas. So imagine that, like you are basically doing lock-free allocations, just incremental. And then goes reclamation. You have tracing, because OpenJDK garbage collectors are tracing. So you have the live data that's referenced from the root set. So how can there be a leak? And the answer is right there in the reclamation phase. So remember, you're tracing the live data tree, and then you're going down and starting from the root set, and you're walking down the path, right? So can something go wrong? Well, if you're tracing the GC root, right, who is responsible for, so first of all, what are the GC roots? Here I've listed them, right? Class loaded by class loaders, your static fields, your threads, your JNI local and global. Who is responsible for these? You, the application developer, right? You have either done the static fields, or you are responsible for the threads. You are doing some JNI local and class loaded, of course, all class loaders, right? You wrote that program, you designed this thing, so you are responsible for the GC roots. So, of course, not surprisingly, Java memory leaks can be actually identified in tracing the GC roots. So there are class loader leaks, there's mutable static field leaks, there is thread leaks, JNI memory leaks, okay? What are the tools that we can use? You have the GC log files, of course, and I have some quick example that I'll give you over here. I'm just being cautious of time. Then you have heap dump, heap profiling, just get live object retention information. Again, there's some of the tools that I've used and I still use. Again, specifying just the terminologies with respect to GC stats that we are used to. Not talking about the coding, the GC unified logging code here, just so that you can translate it as you get chance. Now here is a system, and this is CMS. This system had a memory leak, and when we're looking at the plot, and this is of course just one of the plots. This was not the one. This also helped identify the leak. But what you see here is the live data. Like the live data is increasing. So the live data is from here all to here. The thing in yellow is your old generation occupancy. You see how your old generation occupancy just keep increasing, and right here you're basically getting back to back concurrent mode failures, old gen issues, and you're encountering like just not able to grow and just having a storm of full GCs back to back. And this application itself had a memory leak, and it had it in the class loading things that were happening and lingering around and everything. uh, this is just from the GC log. Of course, we verified it with various other things, but and we sized the heap appropriately, because you have to make sure that you can accommodate the live data, right? So if the live data is really it may not be a memory leak if it's your live data is just big enough and cannot be accommodated in your old generation. But there was various experiments done, and this is just one of the logs that beautifully showcases the leak.
Monica, thank you for the
Yes.
fantastic speech and real cases with memory leak. Your insights were very useful. And thank you for joining us today on our conference. Hope to see you on the next conference. Thank you.